suppose we have this. Okay, we have a number line. We have some people on different points. Let's say some numbers. Okay.
Let's say 1.
Okay, 1.
1.5. 4.
4. Okay, this comes logarithmic scale here.
Okay. Now let's say, I don't know, 5.6. 7.
7. Now on each of these numbers, there is a little person here. They want to travel to some common position. We don't yet know what common position it is. They're going to travel. Let's say these are kilometers, and they want to travel as little as possible. So the sum of all of these traveling should be as little as possible, right? To save gas, save some petrol, right? Okay. So let's say that. So we want to travel to find some, like, where would you guess that? Like, I mean, you would probably know, right? Where would they end up all? But let's say, where is the most like logical sense that they will all end up in?
Well, I don't know. Maybe can I guess?
Yeah.
Maybe somewhere between 2 and 4.
Yeah, exactly. So let's say that the most logical sense is to end up here, right? To end up between 2 and 4. Let's say with 3. So if they all end up here, this guy will have some cost, which is 7 minus 3. This guy will have 5.6 minus 3, 4, and so on. This is 3 minus 1. So like these are the costs of all of these. So how are we gonna mathematically write this, right? Each guy, we're going to say that he's xi. So xi is just x1.
He's at this position, or
what do you mean?
He's at this position.
Yeah, he's at this position. Yeah. So xi is like x1 is the position of the first guy. X2 is the position of the second guy. So this here, let's say x1, x2, x3, x4, x5, x6, right? So this is xi. So what we want is, and this some number here, let's call it x. We don't know which is the most optimal solution, right? So what we want is the absolute, the difference between xi minus x in the absolute value, because we don't know if it's left or right. The sum of all of this should be minimized. Now, it's not really clear where would you put that x in, like, that absolute value. It's not helpful, I would say that. So yeah, let us put this aside and let's see. We're going to think of a number line where you have these xi points, doesn't matter where. Let's say the position that we pick is, I don't know, let's say somewhere here. This is like the distance, right? Now on the left side, we're gonna have like some k number of points. Okay. On the right side, there is n minus k points, because we know like how many points are on the line, how many people are there. So n minus k.
N people, right?
N people, yeah. Okay. N people with like k points on the left and n minus k points on the right. If I move this destination, so I move this destination 1 unit to the right. So what happens with 1 unit to the right? This person spends 1 kilometer more, and this person spends 1 kilometer more. But all of these n minus k persons save kilometer. So in turn, we have 1 kilometer spent on k persons, and n minus k persons save this 1 kilometer. So we want to find such a position that when you move to the right or to the left, no one gains. So it is not optimal to move to the right or to move to the left.
And no one loses.
And no one loses, yes. No one gains, no one loses, because this is going to be the most optimal position for all of them. So which position is that, right? So with little to no algebra knowledge, you can just do, yeah, I want the difference, I want them to be equal, first of all, right? Okay, I want them to be equal, because no one gains, no one loses, right? And then I just do this, and you see that k has to be n divided by 2. So it has to be half of the people have to be on the right side, and half of the people have to be on the left side.
So this is equivalent if we say k minus n min minus k equals 0, right?
Yeah, this is equivalent. So the difference between those people has to be 0, right? So they have to be equal, right? So you see that half of the people are on the left side, half of the people are on the right side, right? So imagine you have an odd number of people. So you can't just put half of the people on the left, half of the people on the right, right? There will be one person which is on the middle, right? And that person in the middle is actually the most optimal solution. By that, we call that the median. The median of the array doesn't mean how, like here we have such a wild array, and yet we pick a point which is an integer value, and yet that integer value gives us our optimal solution. Value is in the sorted array, so it has to be sorted. This is very important.
Hi, I'm Ivan. I hijacked Mitko's channel just for a minute to show you more of an algebraic proof for this problem. Let's consider a function depending on the variable x, where x1, x2, up until xn are already given numbers, or as we previously said, the positions of the people on the real line. X is our destination which we want to find in order to minimize the function. First, let's say that the number of people is even. We'll take two consecutive people, xk and xk plus 1, and insert x inside the interval from xk to xk plus 1. Now that we know where x is, we can rewrite the function without the absolute values in the following way. We can reorder the terms such that the constants are first, followed by the variable with its coefficient. We can see that the function will be decreasing if the coefficient n minus 2k is greater than or equal to 0, which is equivalent as saying that k is less than or equal to n over 2. And increasing if n minus 2k is less than or equal to 0, which is equivalent as saying that k is greater than or equal to n over 2. This observation tells us that the function first decreases, reaches a minimum value between xk and xk plus 1, and continues to increase. The minimum value is obtained when the first derivative is equal to 0, or, in our case, when n minus 2k is equal to 0. So, we conclude that the minimum is reached when k equals n over 2. In case when n is an odd number, we have a person in the middle which corresponds to xk plus 1. If we analyze our function on the interval from x1 to xk plus 1, we can see that the function is decreasing since it is of the form f of x equals some constant c minus k times x. Analogous to this, our function will be increasing on the interval from xk plus 1 to xn. This says that the function changes its slope from negative to positive exactly at xk plus 1, and consequently we found our minimum, which happens to be exactly our person in the middle.
So yeah, we prove that this error, we call it error, is minimized by choosing the median. So if there is an even number, well, you say there is an even number, what do you do then? There's no like middle point, right? But you can pick the arithmetic, whatever, you can pick any point between these two middle points, right? And it will still work, it will still give you the optimal solution. So it's pretty cool, yeah.